guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to continue our talk about Bayesian networks, and specifically we want to talk about linear Gaussian models. So actually we saw in previous sessions that how could we represent the joint probability as a graph, and now in this session we want to see how we could represent a multivariate Gaussian in terms of a graph that has some nodes. Okay, and that graph is actually directed graph, and so we could consider that as Bayesian network. Okay, consider an arbitrarily directional acyclic graph. So if you remember that in Bayesian network we don't have any cycle, so we don't have something like this in Bayesian networks. So consider an acyclic graph, means that the graph does not have any cycle, and over d random variables. So we have d random variable, and each node in the graph contains a variable xi, and so this is a random variable, and the distribution of that is a Gaussian. So this has Gaussian distribution. Okay. Now, for the mean distribution of this node, so the distribution of this node is Gaussian. So the Gaussian distribution has mean and variance. So for the mean, consider that, so the probability of xi given, so we have, it had some parent nodes, so given of its parents, it is a Gaussian, and so now it has mean and variance. The mean is actually sum over all parents, and it is a linear combination of the parent nodes. So if I have three nodes as parent of this node xi, I have w11, w12, w13 in here, then I can calculate this, and we have a bias term in here, so we could represent that bias term as B, and the variance is VI. Okay, so this model has Wij and Bi as the parameters, and also Vi. So these parameters controls the distribution, the joint distribution of this model. Now, if you remember the joint distribution, when I write capital X in here, means x1, x2, and xd. So I represent the joint distribution with just a big X. So if you remember that, it is the product over all the variables p of xi conditioned on parents of that node. Okay, now let's take ln from both sides. if you take ln or logarithm, then this side convert to sum. Now because logarithm converts product to sum, so you have p of xi given d in here. Now if you calculate this and put the Gaussian distribution instead of these pxi given parents of that node, then we have sum over I from 1 to d 1 over 2 variance xi minus sum over all parents wij xj minus bi squared plus a constant term which does not depend to x, so we separate that out. Okay, now as you could see, the p of x itself is multivariate Gaussian distribution. So we could actually extract the mean and covariance of this distribution. To achieve the mean of this distribution, we could use a recursively algorithm. So we know that xi is equal to all of the linear combination of parents node plus bi plus the root squared of vi times epsilon I, and in here we could say that epsilon I comes from a zero mean and unit variance Gaussian distribution. So this is a way to write xi. Okay, now if we take, so we know that the expected value of epsilon I is 0 because it comes from a zero mean distribution, and expected value of epsilon I, epsilon j is I, ij, and I is identity matrix, so epsilons are independent, or in other words, they are uncorrelated. It is more accurate to say they are uncorrelated. Okay, now if we take expected value from both sides, we have sum over all node parents wij expected value of xj plus bi, and the expected value of this term is 0, so we will end up with something like this. And we know that the expected value of x, which is the expected value of joint distribution, is expected value of x1, the expected value of xd transpose. So at first you could actually derive the expected value of x1, then for x2 you know that it is a linear combination of x1, so you could after x1 you could derive the expected value of x2 and so on. And for covariance, similarly for covariance we could do the same thing. So the covariance of xi and xj is expected value of xi minus expected value of xi times xj minus expected value of xj. So we could write it as sum for all parents w jk covariance of xi xk plus I ij vj. So this is how you could derive the covariance of that multivariate Gaussian distribution, and you could do the same like the deriving of mean in a recursive manner. Okay, let's consider an extreme example. In extreme example, let's say our graph does not have any link. In this case, we don't have any wij, so we have just bias. So the mean of the multivariate Gaussian distribution will be B1 to B D transpose, and the covariance will be diagonal, and it is V1 to VD. So in this case, you will end up with D independent univariate Gaussian distribution. Okay, let's see another example. Let's say our graph is like this. So in this case, you could actually derive that the mean of joint distribution is B1. So the B1 is expected value of x1. Now you have B2 plus W21 B1 for the second node, and for the third node you have B3 plus W3 to B2 plus W3 to W21 B2 transpose. And also for covariance matrix, so you know that we represent the covariance matrix with capital sigma. So we have V1, W21 V1, and W3 2 W21 V1, W21 V1 V2 plus W21 V1, and this squared, and W32 V2 plus W21 squared V1, and W32 W21 V1 W32 V2 plus W21 squared V1, and V3 plus W32 squared V2 plus W21 squared V1. So now in this graph, I could actually derive the multivariate Gaussian distribution parameters. So now you learned how to build a multivariate Gaussian distribution with a Bayesian network that each node has univariate Gaussian distribution. Okay, now we want to talk about conditional independence. So we know that independency and conditional independence is actually an important concept in probability theory. So if let's say we have three different random variables a, b, and c, assume that we have p of a given b and c is equal to p of a given c. In this case, a is conditionally independent of b given c. Okay, so we could actually express it in another form. So it is very common to express it and write it in another form. So we could say that p of a and b given c is equal to p of a. So using the product rule that hopefully you now learn how to use it, p of a given b and c times p of b given c, that is equal to p of a given c times p of b given c. So in this case, you could see that the joint distribution of a and b given c is actually can be factorized into two conditional distribution of p a given c and b given c. So in this case, we say that a and b are statistically independent, and we show it with a b given c. So in this case, it means that a and b are statistically independent given c. Now, what does that matter for us? Actually, the conditional independence could simplify the graph for us and has so much interesting properties in the graph. And actually, for determining that whether a graph has conditional independence or not, we could use the separation method. D means for directed graph, and that we will see later. Okay, now before we go for the separation, let's go through 3 examples. Let's say we have this graph. So we have C, B, and A in here. Now for writing the joint distribution, hopefully now you could write the joint distribution P of C, P of A given C, and P of B given C. Okay, so if you write the P of A and B, you could marginalize the C from here to obtain P of A and B. So P of B conditioned on C times PC, which is this. So actually you could see that it is not in general equal to P of A times P of B. So A and B are not statistically independent given, so in here we don't have any condition. So in this case we represent that by phi, which means that we have given to empty set, which is nothing. Actually you could have maybe you find a distribution that it is this equality holds for that, but in general it does not hold for the general case. Okay, now let's say we want to condition that on C. So now we observed a value of C. So I shaded it. And now I know that P of A and B given C is equal to P of A, B, C over P of C. So I know that, actually we know that from the probability session that we had, and we could write that as P of A given C times P of B given C. So in this case, you could see that A is actually independent. A and B are statistically independent given C. Okay. Now let's see the second example. In second example, we have this structure. Okay, if we write the joint distribution, we could write that as P of A times P of C given A times P of B given C. Okay, if we write P of A and B, we could marginalize C from this equation and write it as P of C given A times P of B given C. And now we could simplify it to P of A times P of B given A. And as you could see, it is not equal to P of A times P of B. So in this case, A and B are not statistically independent, given phi. So it means that the empty set. But if we now we want to observe this C, and now we want to see the conditional joint distribution. So I have P of A and B given C is equal to P of A, B, C over P of C. If you write that, it is P of A, P of C given A, P of B given C times over P of C. It is equal to P of C, P of A given C times P of B given C. So as you could see now, I have the definition of statistically independent C given C. So A and B are statistically independent given C. In other words, we could actually get some insight from this graph. When we observe this data, then it somehow blocks the path between A and B. So A and B will be independent. But when we have not seen the value of C, they are not independent. Okay. For the third example, let's say we have A, C, and B. Okay, let's say A, B, and C in here. Now we could write the P of A, B, and C as P of A times P of B times P of C given A and B, right? So we could write P of A and B as P of A times P of B. So A and B are statistically independent given empty set. Now let's say we condition that based on C. So we want to know P of A, B given C we could do the same thing. P of A, P of B, P of C given A and B over P of C, which is not equal to P of A, P of B. So A and B are not statistically independent in this case. Okay, let's see this by an example. Now we want to get some insight about the meaning of this, or how could we gain some intuition about these. Okay, let's say we have 3 random variables. Each of them is a binary random variable. Assume that B is actually showed that a battery state. So if the battery is charged, it is 1. If the battery is flat, it is 0. And F is actually the fuel tank. If it is 1, means that the fuel tank is full, and if it is 0, means that the fuel tank is empty. And G is fuel gauge. So if the fuel gauge is full, it is 1. If it is empty, it is 0. Okay, now let's assume some probability to give some scenarios. P of B equal to 1 means that probability of battery is charged is 90%. The probability of full fuel of tank is 90%. The probability of gauge equal to 1, meaning that gauge shows full, conditioned on battery is full, and the tank is full is 80%. The probability of gauge 1 B1 F0 20%. The probability of G1 B0 F1 is 20%, and the probability of G1 B0 F0 is 10%. Okay. Now let's say before we observe any data, we have a prior on F that the fuel tank is empty is 10%. So this is our prior, means that we have not observed any data yet, and this is our prior. Now let's say we read the gauge as empty. So we read the gauge. So this is, let's say this is the gauge. Here is 1, here is 0, and the gauge is 0. So if this is the fuel sign, and so it is 0. Now the probability of gauge is 0. We could write that as sum over all of the possible states of battery and all of the possible states of fuel tank. P of G equal to 0 based on B and f times p of b, p of f. If we calculate that, we will end up with this number. Okay. And if we want to calculate the gauge is 0, conditioned on fuel tank is 0, we could actually use again this equation, which we will end up with 81% approximately. Okay, now we want to know what is the probability of fuel tank is empty, given that we have read the gauge shows fuel tank is empty. If we calculate that, we could use the Bayesian theorem. We calculate this in here. If you just do the substitution, you will end up with approximately 25%. And if you read it carefully, you will see that it is greater than our prior. So we see the evidence of gauge shows 0. Our probability on fuel tank is empty now improved. So it is 25%. It was 10%. Now let's assume that also now we know another thing. Now we know that the battery also is empty. So in this case, we want to know what is the probability of fuel tank is empty based on two observations of gauge shows empty and also battery is empty. And just note that we know that the gauge something that gauge shows related to the battery status. So if we don't have any battery, then the gauge shows probably the false value. So now it is interesting to obtain this probability. If we write this, we could simplify this as over P of G equals 0 conditioned on. So we will end up with approximately 11%. So in this case, now we know that the battery is empty, so the probability in comparison with just reading the gauge is now lower, but still it has some information and it is greater than our prior because it has some information. But as you could see, now we have some insights about what does these graphs mean and how could we analyze them. So in the next session, actually, we will see how to use d-separation to know the conditional separation, and also we will introduce to another kind of graphs which we talked about, that Markov random fields. And yeah, that's it for this session. Hope to see you in the next session. Bye.